squared. Or
A1 squared. Oh, A1 squared means A1 times A1. This is a matrix product. Times D squared, D switch squared, and so on. And what about the other matrix we have over there? So we have e to the A2, 1 minus d, this switch. It's the same story. I plus A2 times d times this switch, times 1 minus d, plus 1 half A2 squared times d squared, this switch squared, plus how many terms are there? Over here? 2 many. And we have to multiply this equation times this equation. That is exactly what we did for the scalar case. But the scalar case was okay because it was right. It was one of the good properties of the scalar exponential. And if we multiply these two, here it becomes critical, but we have e to the a, 1d plus a2, 1 minus d, this switch, is equal. Be careful that this is critical. Mathematically speaking, you have to use, to invoke big theorems to do this. You have to multiply this infinite series times this infinite series. It's really hard. It's very hard because you have to check if you can do it. We can stop our infinite series over here, so we just take the first terms, and we have I times I is, don't tell me I squared this because it's still I, plus we have I times this term, plus I times this term, that is just this plus this. A1 d this switch plus A2 1 minus d this switch.
Is it 1 minus d squared in the third term of the seventh equation?
1 minus d squared, sure. Plus what? Well, higher order terms. I times a2 squared plus I times a1 squared with coefficients, various coefficient, plus a1, a2 times d, etc., etc. So we still have a lot of terms. Let's go back to the first lecture. Do you remember what I told you in the first lecture? We will make some assumptions to analyze our circuit. The time. Cyclostationary, well, not anymore. We are just moving, changing our input voltage, our duty cycle. So, cyclostationary, just okay.
no output ripple.
No output ripple, okay.
Time constant less than time.
Aha. Time constant on my circuit are far, far longer than the switching period. Here inside, there are the time constants. Inside A1 and A2. The reciprocal should be the inverse of these matrices as a time constant. But A1 and A2 contain inside them the time constant multiplied by the period of time that this time constant is applied. That means that this is a small term, matrix, speaking in terms of matrix. It means that when you add more terms over here, for example, you could add A1, A2, this is one of the possible higher order terms, D1 minus D, this switch squared. You have this switch squared and the product of these two time constants. If this switch as a time constant is far, far larger than this is the square of the same inequality, and this is even more large, even larger. So we can neglect these higher order terms if my time constants are quite longer than the switching period. So the product of my two exponentials, this times this, is not equal to, but it's approximate, a good approximation is I plus the first term plus the second term. And this is commutative. This is what I need to say that the product of these two matrices is equal to E to the average of the matrices times the switch. So, generally speaking, I cannot use the technique of averaging the matrices and say it's okay if my time of observation is quite longer than that, time constant. But here, my time of observation is short. I have no exponential function. I have just straight line functions. And with straight line functions, that is these functions, system works. So that hypothesis I made at the very beginning of this course is still used over here. I need it to be able to make this problem. And it's not just bad approximation. It's not saying, yeah, it's not good. It's a good approximation if you design a good converter. So, we have at the end that this is my differential equation. I average over one cycle the two differential equations for the two states, and I get this equivalent differential equation. What did I lose? Getting up peak values, RMS values. What do I get still? What did I keep? Average values. What did I lose from the frequency point of view? Everything that happens above 1/2 of the switching frequency. Okay? So far so good. Basically what I do here is I use a moving window that is this switch second long, and I move it across my solutions, and moving this across my solutions, I get the average. I also want to move one. Do you like block diagrams? Okay, what do I do over here? I just take a window that is this much long, and this window is moved along the tank. So I have a block that is basically a window that is long this width, and I move in time this window across my system, my variables. And this is just a window. And then I have to average it. So here I have the differential equation solution. But just across this window, because remember, my differential equation was solved for b, 1 minus b time, a fraction of time, that is just one window. Now, this is my input, that could be x, that is my output, that is x average. Well, this is a map, can be a vector. Do you know what's the Fourier transform of this stuff? What is the Fourier transform of this window?
A SINC function.
SINC function. This is let's take the Fourier transform. This is SINC of 1 over this, which is the frequency, times 2 pi divided by 2 is, in general, is omega t switch over 2 over omega t switch over 2. And don't remember if there is this 2 factor over here. But the SINC of this window, this window has a SINC, and this is still multiplied by e to the j omega t, and this is t, the delay. This is just the phase factor, but just forget this phase factor. Sine, omega t switch over 2 times over omega t switch over 2. Okay, SINC has zeros, because the SINC function is something like this. and it has zeros. Where are the zeros? In frequency domain.
1 over half times
1 over T switch, and then 2 over T switch, 3 over T switch, 4 over T switch, etc. The fact that I average over T switch means that I am cancelling with these zeros the switching frequency, twice the switching frequency, 3 times the switching frequency, 4 times the switching frequency, and so on, all the harmonics. And that means that I am losing the waveforms, because I am just killing all the frequency that compose, that made my waveforms. Anyway, that is just something that could explain why this is the frequency domain explanation why I lose the waveforms, the values, the waveforms, because I'm just cancelling all the frequency of this wave. Okay, now we have to solve I have to solve these equations. I have to solve these equations that I wrote. So my average equation for the boost converter CCM, end of math, we go back to the circuit right now. It's just something like x dot equals 8x plus b nu, and we know that this A is the average between A1 and A2, and B is the average between B1 and B2, and this average is evaluated using the weights D and 1 minus D. So if I want to write down my differential equations, I L and BC dot, I L dot and BC dot equals big A times I LBC plus B average times big P. What's the average matrix that comes from the two states that we found earlier? One matrix is still there. The other matrix was on this blackboard that I cancelled. What do we have over here? We have 0 times D plus, what was the other matrix? 0 times 1 minus D, and 0 times D plus 0 times 1 minus D is 0. Okay. Then we have 0 times D times plus
negative 1 over L.
Negative 1 over L. So we have to take this negative 1 over L and multiply it by 1 minus D. So we have something like D minus 1 over L. I just swap the D, 1 minus D, just to avoid the negative sign. Here we have to multiply D times 0 plus 1 minus D times the term we had in the A2 over here.
1 over C.
1 over C, so this is 1 minus D times C. What about here? We have negative D over 1 over C plus negative 1 minus D over C. So
minus 1
negative 1 over C. This is my matrix representing the average of my circuit. What do we have over here? 1 over L times D plus 1 over L times 1 minus D, that is 1 over L, and here is 0. Yay! This is my differential equation representing the average of my circuit. There are no switches over there anymore. There is no change of going from D to 1 minus D, because this is just a value. This is not a square wave. This D is just a number. It goes from 0 to 1. Oh, I can just show you something very bad. What are the eigenvalues for this matrix?
find
false on my system. What if duty cycle changes? False move. Oops. My system is a bad system if the duty cycle changes between two steady constant values, it goes from 0.2 to 0.3, for example, false my system. That's bad, but it's not yet. The worst is still to come. Is this system of differential equation a linear system or a non-linear system?
the linear time variant. A linear but time variant.
This linear time variant, no, it's not time variant because we have no switches anymore. We don't have to change A. A is there for all my T switches, for all the time.
In each T switch D is constant.
If D is constant, this is linear. But D is not constant because I want to find out the relationship between the output voltage and duty cycle, the dynamic relationship, not just D1 minus 1 over 1 minus D, D over 1 minus D, etc. I want the real differential equation relating I and D, function of time. So if D is a variable and I is a variable, D times I is a nonlinear term. Ouch. Oh, by the way, is this IL and this VC the same that we had at the beginning of our equations? No, those are not the same I current or VC voltage. This IL is not the current through the inductor, it is the average current through the inductor. So, at this point, I should put here an average sign, an average sign, an average sign, an average sign, and here the symbols piled up in a very bad way. So, from this point on, remember, we are talking about averages. And D is also changing. I don't write it as an average for reasons that you will understand next week. If I were a good person, but I am not, considering that D is a variable, I should write D like this. D is not a constant anymore. D now is a variable. Function of times. D function of T. D function of T. So, from this point on, if I want to be a good person, I should write this cycle not as a big capital D, but as a variable function of time. And this. Okay, let's write down this equation in terms of, let's go back to the normal form for differential equation, not the matrix form. And I have dIL by dt, IL average. This is the last time that I write the averages. From this point on, all quantities are average. Equals to what? 0 times IL, 0, plus D minus 1 over L times V average. So, here. D minus 1 over L times VC average. Those averages are function of time. Remember, we are using a moving window. So, this is a DIL function of time. This is VC average function of time. Plus, built in over L average, and here we have dVC average by dt equals to what? Let's write lowercase d minus, no, 1 minus d, 1 minus d. D is a variable. This is the reason why I write it lowercase. Over C times IL average, which is a function of T, plus, meaning minus, 1 over RC times VC average, plus what? Nothing. Because because there are no forcing terms. Linear or non-linear? Non-linear. Why? There is the product of D times IL. There is the product of D times BC. Do we have advantages up to this point? Because disadvantages are clear. We lost a lot of information. Do we have advantages to write down this differential equation besides finding the result I want to find? Sure. For example, if you give to MATLAB this differential equation, MATLAB can solve it far faster, quite faster than solving the two set of differential equations, solving the first, going to the second, solving the second, going back to the first, and so on. Why? Because this is a time-continuous differential equation. MATLAB is not forced to go cycle by cycle. This differential equation can be solved with long steps. If you use a high-order solution system like Runge-Kutta fourth order or so, this can be solved with very long steps. Do you see a circuit over here? Not anymore. You cannot give this differential equation to spice. We will see other average techniques that maintain a circuit. They average the circuit, they don't average equations. And with this system, you can give the average system, average circuit to spice, and spice will solve your average circuit in far faster than solving the original circuit. If you give to spice the original circuit, you can take 2 hours. You give to spice the average circuit, it takes probably 20 seconds or less. It's completely different. You gain at least 3 orders of magnitude in simulation time. But when you use these equations, you don't see waveforms. You don't see RMS values. You don't see stresses. You see just the dynamic behavior. Okay, so far so good. Well, you told me non-linear. Ouch. Can we apply the Laplace transform over here? Not in an easy way. So we have to carry on the second step. And the second step is linearize. We have to linearize it. How can we linearize these equations?
Considering a small step around the
Considering a small variation around
duty cycle. Duty cycle.
Duty cycle around BC, around IL, around all the variables. Here the variables are IL, BC, Vin, and duty cycle. So we have to take small steps around this steady state, around these DC cyclostationary values. How can you do this?
Small signal model.
Small signal model. How do you do it? There are two possible techniques. They are exactly the same, absolutely equivalent, but they look different. One possible technique, and we will use it, is take the Taylor series of your system and just remove the high order terms, and just remove the DC, and what we are left with, the first order term is your small signal. Or we will use a different approach over here. For each variable, oops, we got it. Who has a screwdriver? I am sure that good engineers have at least a screwdriver. I can make this substitution for each variable. Let's say IL, that is an average, but from this point on I will forget, I won't mark it as a variable anymore. IL is equal to its DC value, capital IL, plus a small signal value that should be, if I was in circuit theory class, whatever was my class, which is good electronics. I should write it as lower IL with a lower substrate. Here, our electronic guys do different. They write IL with still the same subscript, and they put a hat on top of the value. This is the DC value, and this is the small signal component, and this is the total value. So we have to substitute in this equation for each variable something like this. Instead of D, we'll write D plus D hat, capital D plus D hat, instead of BC and so on, same stuff. So I really need this handle. So I get, be careful because if I make a mistake over here, we will invent a perpetual motion or something else. D I L plus I hat L by dt equals 1 minus D minus D hat. Instead of D, I write D minus D plus D hat over C. Oh no, I am writing the second equation, sorry. You see how to make bad mistakes? I have to read the first one, that is D plus D hat minus 1 over L times VC plus VC hat plus big in plus big in hat over L. And this is the first. The second is D times big VC plus VC hat differentiated by dt equals 1 minus capital D minus D hat over C times big IL plus IL hat minus VC plus VC hat divided by RC. Linear or non-linear?
Linear only
It's not linear. Non-linear. Linear only if D hat is 0. But if D hat is 0, I am not controlling my system. So D hat is that. So the product D hat times I hat is the non-linearity in my system. What kind of terms do you get from these when you multiply out, work out these products? You have terms that are something like D times capital D times capital I hat. What kind of a term is it? This is the steady state, the constant D part multiplied by the constant IL part. What's that?
the working point.
Working point, bias point. Then we have, for example, D hat multiplied by big IL. What's this? D hat times a constant. That is a small signal term, small signal component. Then we have D hat multiplied by I hat. What kind of a term is it? Non-linear, second order. If I hat equals I hat plus I hat L, if I hat L is smaller, far smaller than capital I L, and this condition is the small signal condition. When I multiply two small signals, each other, I get a second order result that I can neglect. So from this equation, I get three kinds of terms. I get DC terms. I don't neglect them. I remove them. Then I get low signal, small signal terms. That is what I am looking for. And then I get second order terms. I neglect them. I neglect because if it's a small signal, the second order term can be negligible, is negligible with respect to the other terms. D hat times I hat is small compared to D hat times big IL, because big IL is far larger than I hat. So, three terms, DC, small signal, nonlinear, second order, negligible terms. The DC terms, I remove them. I don't invent them, I remove them because it's a different country. Then small signal is what I'm looking for, and then second order integration. Okay? Let's write down just as DC terms, and then we take a break. Just the DC terms I have. DIL by dt equals, tell me please. D over F times VC plus minus plus. Are we looking to this one? So it's D minus 1, it's not D times VC. Because 1 over here is a constant term. So the constant is D minus 1 times VC. D minus 1 over F times VC plus VC hat not there, plus being over there. And the second one is dVC capital by dt equals 1 minus d over c times IL minus d over c times IL plus meaning minus VC, capital VC over C. Can you solve this? How much is the derivative of constant? This is a constant. How much is the derivative of constant? And so L and L cancel out, C and C cancel out. What do we get from the first equation? We get VC equals
minus 1 over minus 1 over D minus 1 and D out over D.
I move this D minus 1 over times VC to the left hand side. I get 1 minus V times VC equals V. And so VC equals V equals 1 minus D. This is the steady state solution. Well, better if we solve the steady state solution the other way around, because this takes a lot of time, a lot of calculation, but this is just a check. And we can also write this as V in equals VC times 1 minus D. That's very difficult. I just inverted it because I need being right now. What about the second one? What do you get from the second equation? You get VC over R equals IL times 1 minus D. That means VC over R times 1 minus D equals IL. Did you already see this one, this equation? What is VC over R? Output current multiplied by M, 1 over 1 minus this M, gives you the input current. That is just a DC standard equation that we derived a long time ago. And let me write it in a different way. This is IL is equal to V in over R times 1 minus D squared. I just transformed the VC into V in because I need V right now. Yeah, up to this point I didn't make too many errors. There are still possible errors around, but up to this point we found a result that we already knew. After the break, we had to solve these equations for the variable term, of the linear term. That will be a little bit longer, but eventually we'll get the final. Okay, let's take a break.